Recording in progress.
So, good afternoon, everyone. Welcome to this talk on galaxies. My name is Yogesh Wadadekar, and I work at the National Center for Radio Astrophysics in Pune. And I'm going to be giving you two lectures on galaxies. The first lecture is going to be today. It was supposed to be on Monday, but since I'm going to be out of town on Tuesday, I've preponed the lecture, one of the lectures, so that we can be done on Monday afternoon. Okay, so let's begin. So here's a rough outline of the two talks, in fact. Uh, Galaxy morphology is something that I will cover in some detail. I will also talk about galaxy groups and clusters, which are the structures larger structures which galaxies form. We will talk about galaxy dynamics and how that has been used to detect and study the properties of dark matter. We will look at galaxy mergers, which are particularly important in forming the galaxy morphologies that we see today. We will talk briefly about the last three topics: gravitational lensing, and how that is important to studies both of galaxy evolution and of galaxy clustering. We will talk about how mass, distance, and luminosity of galaxies are measured in the real world. And very briefly, I will talk about active galactic nuclei and supermassive black holes at the centers of galaxies. And that is because Vaidehi is going to be giving you a full set of lectures on active galactic nuclei. So let's begin. So the study of galaxies is a very, very active field of research today. Uh, about 25% of papers published in astronomy, as referenced on the ADS website in 2021, were on galaxies. And there were about 8,000 refereed papers. Okay. This is a very prodigious number. So, out of the 32,000 or so total papers written in astronomy, 8,000 of these were on galaxies. So it is not surprising that since 25% of the papers are on galaxies, about 25% of researchers worldwide work on problems related to galaxies. Most of the things that are going to be covered in my lectures were discovered in the last 20 years. And this is also an expression of the fact that this is a very active field of research at the present time. Okay. So, so before we head there, if you want to learn more, uh, I have a full 21 lecture course which is available at this URL. You may note it down if you like. And this course contains lecture PDFs as well as recorded videos and also assignments. So this forms a very complete set of materials which you can use for a very detailed study of galaxy morphology, galaxy formation, galaxy evolution, and also a bit of galaxy dynamics. So I'll refer you to that right at the very beginning. And several of the slides that I'm going to be showing you today are extracted from these 21 lectures. Okay. So if you look at the universe, you see that in order to understand the universe, you have to understand three ubiquitous structures, three building blocks of everything that there exists in the universe. These are atoms, stars, and galaxies. And in turn, these three things depend on each other. So, for example, if you want to understand stars and how they behave, um, and how they change with time, you have to understand atoms. Particularly, for example, you know that it's nuclear fusion that powers stars. So you have to understand what's going on in the nucleus of hydrogen atoms, fusing into helium and so on, before you can begin to understand what stars are like. Similarly, galaxies are composed of stars, and therefore, in order to understand galaxies, you need to understand stars very well. Probably in the next lecture, we will talk a bit about stellar population synthesis and how that is used to understand the properties of galaxies. The galaxies themselves can be treated as the building blocks of the entire universe itself. So just like atoms are the building blocks of all the matter that we see around us, galaxies are the building blocks of the universe on the largest scales. On the largest scales, you know that they form clusters and superclusters, and they form what is called they trace what is called the cosmic web. And for these reasons, the study of galaxies becomes very important. So, if you want to construct the uh, the first thing that people try to do when they realize that we are living in some kind of large structure, which we today call the Milky Way galaxy, they try to infer its shape by doing stellar counts. And way back, more than 200 years ago, this was attempted by William Herschel. So what he did was he basically pointed his telescope in different parts of the sky and began to make counts of the stars that he saw in various directions. Okay. And so the claim was that in directions where you saw very few stars, there the galaxy, in those directions, the galaxy did not extend very far out. But places where you saw lots and lots of stars, perhaps that was the center of the galaxy, and so on. But he was hampered by the effects of dust. And dust is really quite common, especially in the disk of our galaxy. And there are situations where the dust extinction is so high that you simply cannot see the stars that are lying behind the cloud of dust. And in such a situation, trying to trace the three-dimensional shape of the Milky Way was next to impossible. But fast forward to today, and we can do much better. Recently, a space telescope was launched. Its name is Gaia. Uh, and what it basically does is that it does astrometry and photometry, and it also measures radial velocity of the stars using a spectrograph. So what it can therefore do, it can calculate via the astrometry, it can calculate the exact X, Y, Z position of the sky. What it also does with the astrometry is that it can determine how fast object is moving in the transverse direction, a particular star is moving in the transverse direction by measuring the proper motion. And by using the radial velocity, it can calculate the uh, 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 how fast it's moving in the radial direction. So by doing careful modeling and by using the astrometry and the photometry, it becomes possible to calculate uh, 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 the entire phase space diagram with all six components of these stars. You would ask, how is the distance measured? The distance is measured in this experiment using the parallax effect. So because of the Earth's orbit around the sun, the apparent position of a star changes over time. And by measuring this systematic motion of distant stars, one can measure their parallactic distance, which is a very simple geometric effect. And with a very sensitive astrometric telescope like Gaia, it becomes possible to measure the proper motion to very, very high accuracies. So once you have that, so what is shown here in this figure are the trails of about 40,000 stars within about 300 light years of the solar system, and how each star is going to move over the next 400,000 years. Now, you may ask, how is this calculated? Because we know X, Y, Z positions of each star today. We also know Vx, Vy, and Vz, the three components of the velocities in these three directions. But how do we know whether they will continue to move at the same velocity? In fact, we know for sure that they won't continue to move with those same velocities. The velocities will change depending on the dynamical properties of the system, which means what one needs to do is one needs to take all of these stars at these various positions and various velocities and calculate the net potential of these stars. While doing that, you have to take into account the dark matter that exists in the Milky Way. But if you build a map of the potential at every point in the galaxy, then you can solve Poisson's equation and find out what are the forces that are operating on these objects, on these stars, what acceleration each star will face, and therefore how its velocity will change as a function of time. And you can do this in progressively in different time steps, and you can calculate the future positions of any star in the galaxy. So this is really, really a big step up from what Herschel had achieved. In fact, it's a big achievement for Gaia itself, because all of these things that I'm talking about over the last 3 minutes were simply impossible to do without the Gaia satellite. And the Gaia DR3 contains as many as 1.8 billion sources. Most of these are stars, but they also include some distant galaxies and quasars, which don't move, which don't have any proper motion, and therefore can be used to tie down the absolute astrometry of the system. Okay. So now that we have all of this information, Gaia is able to reconstruct for us a map of the Milky Way galaxy as it exists today. So the Milky Way, as many of you probably know, is a spiral galaxy. Okay. And not only is it a spiral galaxy, it is what is called as a barred spiral galaxy. So there is a bar, a central bar, which exists there. Okay, there is a bar which is there at the center of the galaxy. And at the end of each bar, you have a spiral arm which is coming out. Okay, so this one of the arms is called the scutum centaurus arm. Okay, and then there is the Perseus arm, And also there are spurs. By spurs, one means arms that come out of another parent arm. Okay. So, for example, this outer arm that you see here, okay, is a spur of the Perseus arm. And also there is now a new outer arm which has been rediscovered or discovered with Gaia. Similarly, a spur of the scutum centaurus arm is the Carina Sagittarius spur. And so, therefore, although there are two main arms, there are different star forming regions in the disk of the galaxy, in the plane of the disk. And all of these have been now mapped out. The sun's orbit is also shown here. It goes around like this. Yeah. And all of this has been mapped in enormous detail using those 1.8 billion sources whose properties have been measured by the Gaia telescope. Okay, so what are stars? Okay, uh, so what are galaxies? Sorry, galaxies are agglomerations of four things: stars, dust, gas, and dark matter. Okay, and uh, if you ask the question, in what ratio are these three things there or four things there, you can say that the average mass ratio of gas to stars to dark matter is roughly 1 is to 10 is to 100. So clearly, dark matter is mass wise definitely the dominant component of the galaxy, or of galaxies in general, followed by stars and gas. The dust usually, although it has a high impact on the visual morphology of the galaxy, in terms of the mass of the dust, it's usually a much smaller fraction than the gases. Okay, so you have gas, you have stars, and you have the dark matter as the dominant massive components of the galaxy. And galaxies, as I mentioned already, are the basic building blocks of the universe on the largest scales, and they show a very broad range in their physical properties. And therefore, understanding of galaxy formation and evolution is one of the main outstanding problems in modern cosmology. There are of the order of 10 raised to 11 galaxies in the observable universe, and they range quite widely in mass. They range all the way from about 10 raised to 8 solar masses to up to 10 raised to 12, or sometimes even 10 raised to 13 solar masses. If you look at the history of the study of galaxies, that's a very interesting one. So I'll spend a few minutes discussing that. Way back in 1755, Immanuel Kant, who was a philosopher, he wrote a book called General Natural History and Theory of the Heavens, in which he made the following points. He said that the Milky Way is like a huge solar system. It's rotating, and its origin is from the rotating cloud. Uh, all of these things he said. Then he also said stars far from the disk's plane do not go around in circular orbits, but are on different orbits. And disks, like the Milky Way, project to ellipses uh, when uh, when looked at from a different viewing angle. And at that time, an astronomer named D. Maupertuis had looked at what are called oval nebulae. Okay, we call them elliptical galaxies today. And he said these are also what he called island universes. Now, how Immanuel Kant, uh, before many discoveries about the universe, how he could have surmised so many things correctly about the Milky Way galaxy, and about other galaxies in general remains one of the big surprises. After that, of course, people did look at several nearby galaxies like M33 in Triangulum and the M51 galaxy and so on. But they always thought of these galaxies as nebulae. So, you know of the Orion Nebula, which is a giant cloud of hydrogen, a big star-forming region in our galaxy. They thought that these galaxies were also nebulae, gaseous nebulae. It was in 1912, using the newly discovered spectroscopic techniques, that Slipher discovered that nebulae are rotating. Okay, and then people started thinking, why are they rotating? Because the Orion Nebula and Crab Nebula and all these other nebulae don't seem to be rotating. So why is this thing rotating? And then in 1920, a debate was organized, because when people discovered this, some people started saying that these galaxies are not actually nebulae, but they are independent island universes lying outside our Milky Way galaxy. And so in 1920, a debate was organized in Pasadena between two famous astronomers of the time, Shapley and Curtis. And the topic of the debate was, are spiral nebulae island universes? And there were 30-minute presentations by each of these two speakers. And after that, they held a vote amongst the other astronomers who were present and asked them, what do you think? Uh, Shapley was the one who said that these galaxies are within our galaxy, or these spiral nebulae are within our galaxy. And Curtis said, no, they're outside. And Curtis was right, but in the democratic vote of astronomers, Shapley won, but not for very long, because by 1925, Edwin Hubble had reported the discovery of Cepheid variable stars in the Andromeda galaxy. And if you calculate the distance to these Cepheid variables, then they are more than, they're clearly so far away that the Cepheids in the Andromeda galaxy cannot be part of our galaxy at all. And therefore, the Andromeda galaxy itself is an independent system lying outside our own galaxy. So it's because of this, one should keep in mind that extragalactic astrophysics, or the study of external galaxies, is a subject which is less than 100 years old, although it will turn 100 in a couple of years. Okay, so even before people realize that these galaxies are independent island universes, people had started making catalogs of galaxies. Messier made a catalog of 109 nebulae, so that comet hunters wouldn't mistake them for comets. And about 40 of these, okay, about 1/3 of them were galaxies. In 1888, a new catalog of galaxies was constructed called the New General Catalog. It had more than 7,000 objects, of which about half were galaxies. These NGC 4993 is one example. It's only about 40 megaparsec away, where the first gravitational wave neutron star merger was detected in 2017. In the 20th century, many catalogs like the NGC were produced, the Uppsala General Catalog or the RC3 catalog, etc. But nowadays we have automated digital surveys. Okay, you have most famously the Sloan Digital Sky Survey, SDSS for short, with tens to hundreds of millions of galaxies. Okay, so now of course, if you ask the question, how should we label them? Obviously, you can't label them with a number, because then the number will become very long. So instead, one chooses to label these galaxies by the right ascension and declination on the sky. Uh, Coming very soon, which means within 2 years, ambitious new survey will start, which is called the Rubin Large Survey of Space and Time. This will provide photometry for more than 10 raised to 10 galaxies, about 20 billion galaxies is the estimate, all the way from the local group to redshifts greater than 6. And it will provide useful shape measurements and 6-band photometry for about 4 into 10 raised to 9 galaxies. Okay. So whenever you do study any kind of new object, first step is census. Second step is classification. We'll look at that when we talk about morphology in a minute. And the third step is understanding. Okay. Uh, for the classification problem, Hubble proposed a scheme for classifying galaxies. Uh, his scheme is called the tuning fork diagram. It was first proposed in his 1936 book, The Realm of the Nebulae, and the scheme survives in its essence to the present day. And the four main morphological types, ellipticals, lenticulars, spirals, and irregulars, are sort of the backbone of this tuning fork diagram. However, now that we are studying galaxies using a variety of different techniques, a better approach may be to look at the properties of kinematic subsystems within galaxies. For example, disks and spheroids and halos and things like that, and try to deduce their origins and evolution. Because the kinematics of these substructures captures the diverse merger history of these systems and also captures the diverse star formation history of these systems. Okay, so before we talk about galaxy morphology in some detail, let's take a quick tour of the universe as it stands uh, today, starting with the Big Bang. So the Big Bang, as all of you probably know, occurred about 13.7 billion years ago, a gigantic explosion which occurred everywhere. In the first second of after the birth of the universe, we had a phase called inflation, which you will learn about in some detail in your cosmology lectures. The universe was initially very hot. It was just one hot. All the matter in it was just one hot plasma. As the universe expanded, it cooled. About 400,000 years after the Big Bang, a stage was reached when this plasma had cooled enough for the protons and electrons to come together to form a hydrogen atom. And then what followed for a few 100 million years was what is called as the Dark Ages. And it's in these Dark Ages that uh, no light was being emitted, because there were, of course, the photons from the Big Bang which were traveling through the universe. They're still seen by us today. We call it the cosmic microwave background, but there were yet no stars and no galaxies. But hydrogen, under its own self gravity, began to attract other hydrogen atoms. They began to form giant clouds of hydrogen. There are mechanisms by which these hydrogen atoms could lose energy and cool. And once they cooled, hydrogen atoms could form hydrogen molecules, and therefore giant molecular clouds formed. And within these giant molecular clouds, due to further cooling, there could be some of those giant molecular clouds condensed into small spherical structures, where now the temperature began to go up as the cloud collapsed under its own gravity. Eventually, a stage was reached when it became hot enough for nuclear fusion to happen, and the first stars were born. Now, exactly when those first stars were born is still a subject of debate. When this particular picture was made about 15 years ago, people felt that the first stars were born about 400 million years after the Big Bang. There is now mounting evidence that that is not the case, and these first stars formed much, much earlier, possibly even 200 million years after the Big Bang. These new discoveries are driven by observations made with the James Webb Space Telescope, which was launched about 1.5 years ago. So once the stars formed, these stars, of course, came together or formed actually in stellar clusters. Stellar clusters came together, merged, and formed the first galaxies. And then the galaxies continued to grow by themselves by converting their gas into stars, but also continued to grow by merging with other galaxies to form bigger and bigger galaxies. So, if you want to trace the evolution of the universe from about 400 million years to today, then the stars and their collections of stars, which we call galaxies, are the most effective probe for tracing this evolution. At the late stages, which means closer to the present time, uh, uh, something known as dark energy took over, and that is now driving the accelerated expansion of the universe. Okay, so I'm just going to show you, I hope this works correctly. I'm going to show you a simulation which just summarizes all that I spoke about in the last 5 minutes. So let's try that. What you're seeing here is a rotating box. And what you see here at the bottom is the time since the Big Bang. Okay. At the bottom left corner, you should be able to see it. So it's now about 1.5 billion years after the Big Bang. The first structures are beginning to form, and the first galaxies have already appeared in the densest part of the dark matter structures. You can see that the blue color basically traces the distribution of the matter, and now you can see that there is these giant explosions has begun to happen in different parts of the universe, and these are producing metals in large amounts for the first time. And the metals, which are metal polluted gas, which is colored red in color, that is beginning to spread throughout the universe. We've reached about 6-7 billion years after the Big Bang. After some time, these explosions, which are primarily driven by active galactic nuclei providing very energetic feedback and driving out the gas from outside of the galaxy. Now you'll notice here that much of the gas is now looking magenta in color, indicating that a lot of metals have been created and they have been dispersed throughout the universe and through the intergalactic medium. We've reached about 10 billion years after the Big Bang. Those explosions have stopped. The peak of AGN activity, the peak of star formation activity, all that has come to an end. And now the universe is sort of evolving quiescently. And now we are zooming on to a structure which could correspond to a galaxy cluster in the present day universe, perhaps something like the Coma cluster. So this is work that is done by a very large team of people who work under the name the Illustrious Collaboration. The people are listed here. And this is a very, very complex simulation that was carried out some years ago with a supercomputer. A simulation of this nature runs for 6 months or more, even on the fastest supercomputers on the planet. It's a very giant effort, and recording the data, analyzing the data, and so on requires a large team of people who are fully occupied for a large fraction of that time. Uh, so, so we have now reached the stage where we begin to have a near complete understanding of how galaxies formed and evolved. So now let's move on to galaxy morphology. If you look at galaxies, you may think of them as being belonging primarily to four types: ellipticals, lenticulars, spirals, and irregulars. The spirals themselves may be barred, like the Milky Way. That means they have a bar, or they could be unbarred. So the first morphological type that we will look at are the elliptical galaxies. So this is a picture of a typical elliptical galaxy. Okay, it's basically an egg-shaped object which is bright at the center and fainter towards the edges. Uh, it's structurally very smooth. Okay, it's practically featureless. If you look at it with other kinds of telescopes and measure the amount of gas that it has, you'll find that it has very little of ionized gas. It has very little of neutral gas, very little molecular gas. And also, if you look at it, trying to detect how much dust it has, the elliptical galaxies have very little dust. And also, they have very little star formation. Okay? So these are really what we call red and dead systems. They're red because they're blue stars. The young blue stars within them are all dead. And what survives is only these old stars, which are also low mass stars, which are very long lived stars. All of these survive up to the present time. But elliptical galaxies hide the violent history of their birth. Okay, so elliptical galaxies were believed to have formed the bulk of their stars at early times when the universe was young, and they have undergone a number of mergers to build up the large masses that we see for them today. And if you observe elliptical galaxies with very, very sensitive telescopes, and this is an image made by a scientist named Pierre Duke, who used a very, very advanced camera on the Canada-France Hawaii telescope in Mauna Kea in Hawaii. And he observed so-called elliptical galaxies to very, very low surface brightnesses, to very, very high levels of sensitivity. And he found that almost every elliptical galaxy that he looked at showed these kind of tidal streamers and rings and shells and things like that. These are all stars that have been thrown or scattered out of the elliptical galaxy itself, which is at the center, and they are now sometimes in orbit, sometimes crashing in orbit, but falling back onto the elliptical galaxy and so on. So one should take this first statement that I made, that the light profiles of elliptical galaxies are very smooth with a pinch of salt, because if you go to low surface brightnesses, these galaxies are not smooth by any stretch of the imagination. Now let's jump to the opposite kind of galaxy, which are called irregular galaxies. Irregular galaxies, particularly uh, uh, many of them which are star forming, are like the exact opposite of elliptical galaxies. Elliptical galaxies have very regular shapes. Irregular galaxies are called irregular because they don't have any particular shape. Uh, Elliptical galaxies have very little gas. Uh, Irregular galaxies are uh, often very rich in gas. Elliptical galaxies don't form too many stars. Irregular galaxies form stars in profusion and so on. So, in every way, they are like the opposite of elliptical galaxies. In one sense, they are similar to ellipticals, which is in their kinematics, which we will look at later. Okay. So irregular galaxies, if you zoom in into them, there are two irregular galaxies which are satellite galaxies of the Milky Way. They're called the Large Magellanic Cloud and the Small Magellanic Cloud. And this is a photograph taken with the Hubble Space Telescope of some of stars in the Large Magellanic Cloud. The Hubble Space Telescope has sufficient resolution and sensitivity to actually detect individual stars, even in the Large Magellanic Cloud, which is way outside our galaxy, and uh, and see them. The third type of galaxy that we can consider is what is called as the lenticular galaxy. The lenticular galaxy is something that has a three-dimensional spherical structure or spheroidal structure, which we refer to as a bulge, just like elliptical galaxies do, except that in addition to the bulge, these galaxies also have a very large disk. Okay, and this particular one is what is called as an edge-on disk. The inherent shape of the disk is circular, but when viewed at a different viewing angle, it can appear as a very highly elongated ellipse, as you see here. This particular lenticular contains quite a bit of dust, which you see as these dark or brown or black patches within the disk. And the disk, usually, it doesn't have too many stars, too much star formation in lenticular galaxies. So lenticular galaxies, like spiral galaxies, have two components: a bulge and a disk. Okay. Unlike elliptical galaxies, which have only one component, the bulge. In many of their properties, these lenticular galaxies are intermediate between spiral galaxies and elliptical galaxies. So if you ask the question, how much dust is there in lenticulars? So that is less than the dust, more than the dust in ellipticals, but less than the dust in spirals. If you ask the question, how much gas is there in lenticular galaxies typically? Again, the answer is the same. There is more gas than ellipticals, but less gas in spirals. If you ask the question, how much star formation there is in lenticulars, it is again intermediate between spirals, which have a high star formation, and ellipticals, which have low star formation. Okay. So spirals. So spirals are, of course, interesting to us, primarily because we happen to live in a spiral galaxy. Spirals themselves come in two different flavors. This, what you see picture image here, is what is called as a grand design spiral. Okay, so this is like a Ferris wheel kind of structure. There are lots and lots of spiral arms. The spiral arms themselves are coherent structures extending out to very large distances. The typical size of a large spiral like the Milky Way is about the diameter is about 100,000 light years. or about 30 kiloparsecs. Uh, of course, other spirals are smaller. Bigger spirals are relatively rare, although we know of one bigger spiral in our vicinity, which is the Andromeda Galaxy. Sometimes spirals are unable to form and sustain those grand design spiral arms. In such cases, you may get another kind of spiral, which is called as a flocculent spiral. So in a flocculent spiral, you have the central bulge, which looks yellowish in color, this whole thing. It looks yellowish because it is mainly composed of older stars, and around it are these is the disk of the galaxy, and the disk is punctuated with these sort of bluish structures. Okay, the structures themselves are interrupted with darker regions, which are primarily caused by the dust, and each of these blue regions that you see here, and if you count carefully, there are literally hundreds of them. These Each of these things is a star forming region, which has a small star cluster which has formed. And because this doesn't have very well defined spiral arms, this is not a grand design spiral. It is what is called as a flocculent spiral. If you look at the nucleus of galaxies, then often they show these kind of the nuclear structure reflects the overall shape of the galaxy outside. So the spiral galaxy, this is a spiral galaxy. You zoom in towards the center and you see another spiral. Okay. So this looks quite interesting because this indicates that perhaps the mechanisms that lead to the formation of spiral arms on the larger scales, similar mechanisms also operate on smaller scales. So this kind of almost fractal-like structure is seen in many spiral galaxies. So now we come to the barred spiral, which is the another variant of spiral galaxies. And this is an example of a barred spiral galaxy. Uh, the Milky Way is a barred spiral galaxy, not shaped quite like this because we don't have a very powerful bar. The bar is somewhat smaller, and the arms are much longer and in extent, and they contain a lot more stars, and the underlying disk is also quite bright. But nevertheless, this is a good example of a barred spiral galaxy. The disk of spiral galaxies is not inherently stable. The disk you should think of like a saucer or like a frisbee. Okay, it's a two-dimensional structure. It's inherently circular in nature, and it's only due to projection that effects that we see it as an ellipse. This structure is quite thin, so the diameter of the disk may be 100 times more than its thickness. Okay, and because of this and other dynamical effects, uh, the disk itself, as it rotates, is not stable. Okay, so it wobbles up and down, and this can lead to what are called lopsided galaxies. And this is an excellent example of a galaxy which is sort of going where the disk is going up and down. It's not in a perfect straight line. So we do see several examples of lopsided galaxies like this one. So now we come to the Hubble tuning fork diagram. So what Hubble said was, let me make a diagram like this. There's one handle, and these are the two arms of the tuning fork. And what Hubble did was he placed circular elliptical galaxies at the left, and in galaxies with increasing ellipticity towards the right. At the base of the fork, he placed these S0 galaxies. S0 is another name for lenticular galaxies. They're exact synonyms. And then along one arm, he placed spirals with decreasing bulge and increasing arm openness. And similarly, on the other arm, he placed, instead of regular spirals, he placed the barred spirals. And as you go on, you can see clearly that the sort of spherical component is becoming progressively weaker and weaker. Okay, here also you can see. Here it's relatively strong, it's weaker here and quite weak here. And the spiral arms become increasingly more and more open. So there, this diagram becomes useful for studies of galaxy evolution because there is a clear trend of the bulge strength with the morphological type. And also there is a clear trend of with morphology of the star formation properties. So here is another rendering of the same diagram, this time replacing it with nice color images of galaxies. E0 is still here, E6 is still here, your S0 and SB0 are here, SBA, SBB, SBC, etc. are there. And in his original diagram, Hubble had no space for irregular galaxies. But later variants of the diagram always place these irregular galaxies over here on the right-hand side. And so as you can see, the bulge becomes smaller and smaller and smaller. By bulge, one means this sort of yellowish object at the center. So for ellipticals, it's 100% bulge. For S0, a disk appears for the first time. And as you go to SA, SB, and SC, the bulge becomes smaller and smaller and smaller. In fact, there can be bulge-less galaxies also. We call them many SD type galaxies have no detectable bulge. So this is a trend with the decreasing strength of the bulge. But notice also that the color of the galaxy changes from yellow to somewhat blue to more blue and then very blue. Over here, of course, it's very blue. And the reason that happens is because the amount of gas is increasing as you go from left to right on the Hubble sequence, as also the amount of star formation. So star forming galaxies look blue in color primarily because the light of these galaxies is dominated by the massive O and B type stars which form in OB associations. And these stars are very massive, very luminous, and so on. And because they're very luminous, they have a very high surface temperature also. And because of that, they glow blue in color just by Wien's law. And so that is why these things are blue. Of course, unless the star formation is sustained, uh, this blue color cannot be maintained, because if you switch off the star formation today, the O and B stars that you have formed will die out in a few million years or a few tens of millions of years, and then the galaxy will turn yellow, like the S0 or the elliptic. Okay. So this is the last topic that I will cover today, and then we'll stop. So far I've been talking about galaxies which are relatively luminous. Okay, and uh, these galaxies are included in the main sequence, in the Hubble sequence, uh, on the tuning fork. But there are other classes of galaxies, which we call as dwarf galaxies, which are not part of the Hubble tuning fork diagram. They are low luminosity, they are low mass, they are small in size, typically a few kiloparsec. They're often dark matter dominated, which means the amount of dark matter that they have is higher than the average amount in galaxies. Often they're very low surface brightness, so they're very hard to find. They themselves contain multiple families of objects. They are the gas-poor passive objects, which we call dwarf ellipticals or dwarf spheroidals. And there are the gas-rich star-forming objects, which we call as the dwarf irregulars. Why are these dwarf galaxies important? They're important because majority of galaxies are dwarfs. The massive galaxies are relatively rare. Dwarf galaxies may be remnants of galaxy formation process. Proto-dwarf gas clouds came together to form larger galaxies. And dwarf galaxies are currently being cannibalized by larger galaxies. Dwarf galaxies are also relatively simple systems, not merger products. And in some sense, they can be thought of as pristine low metallicity galaxies. And therefore, they're useful for what is called near field cosmology, which means they can be used to uh, study the kind of uh, uh, galaxies that existed in the distant universe when the universe was quite young, that there were no massive galaxies yet, only small galaxies, dwarf galaxies were there everywhere. And therefore, studying them helps you understand those high redshift galaxies, which you can't often detect and study in great detail as you can do with nearby galaxies. And that's why it's called near field cosmology. So I'm going to stop at this point and I'm going to take any questions or comments that you may have. Yeah. Do you want to sort of just raise your hands and then ask me the question? Would that is that how it's done?
Yes, Yogesh. On Zoom, they will raise hand and I'll unmute them.
Yeah. So I have opened the participant list. So
But I assume there are some people in from joining from the auditorium.
okay.
They should have access to a mic through which they can ask questions.
Okay. I think people are sleepy on a Saturday afternoon. Yeah, there is one Kirti who's raised her hand. Yeah, Kirti, can you please unmute and ask your question?
Yes, good evening, sir.
Yeah.
So my question was, how did Shapley and Curtis argue whether the island universes belong to the Milky Way or outside it?
Yes. Uh, so at that time, there was no definitive evidence in the form of measurements of the Cepheid variable based distances. Okay. So people had tried. So one of the things that the reasons for the debate was that one group of, I mean, whoever was supporting the island universe hypothesis was trying to show that these galaxies are rotating very rapidly. And we don't see the local nebulae to be rotating at all. So that was their main argument. Uh, but they didn't have reliable distances to these galaxies. And there were some other techniques which were used by the other party, which tried to show that, okay, it's fine, these are rotating nebulae, all that is fine, but their distances are not very large. So that was the sort of clinching argument. Uh, which convince most people that these are relatively nearby. I mean, many years ago I've read an article which described this debate in detail. I don't recollect which book it was from, but you can try to Google for it if you want to learn. Any other questions? So if not, we can stop here. And if meanwhile you think of some questions by Monday, Monday afternoon, I'm going to give my second lecture on galaxies. So you can, of course, ask at that time as well.
Yeah, thanks, Yogesh.
Yeah. Okay. So I'll stop sharing now.
Sure.
Yeah.
Recording stopped.
Okay, there is a question on the chat here, which I can answer. How are we sure that the dwarf galaxies are dark matter dominated? That's a very good question. Uh, the way we measure how much dark matter there is in a galaxy is by measuring their rotation curves. And yeah, if these are rotating systems, then if they don't have dark matter, then their rotations are expected to fall down rather rapidly as a function of distance. What is found for these dwarf galaxies that the rotation does not die out at all, and therefore that indicates there must be, you can use how fast the rotation profile goes down to measure how much dark matter there is. And so that's how you know that there is a lot of dark matter. You have to calculate the amount of visible matter. That's relatively easy because you can use a technique called stellar population synthesis to model the star formation in galaxies, and by using the observed fluxes in various bands and as also the spectra of these galaxies, you can build up a model of how many stars there are in the galaxy, and also how much gas and dust there might be in that galaxy. And then using that, so that's your measure of the visible matter. So the ratio is very high. Dark matter to visible matter ratio is very high for dwarf galaxies. Uh, so on what factors the star forming ability of a galaxy depends? Okay, this also is a very interesting question. Uh, as you can see, star formation, what is the raw material for star formation? It's gas. Okay, without gas, if you don't have gas, you have uh, no star formation at all. And so clearly the key ingredient is gas, but also an important thing to consider is the gas cool enough to condense into molecular clouds? That is another variable that needs to be considered. But if the enough gas is there and there are the conditions are right for it to cool to form the giant molecular clouds, then star formation happens. How long it sustains is also another question. So sometimes what happens is if you rapidly form stars, then that also leads within a few million years in the formation of supernovae. And supernovae are very effective in providing feedback and energetically driving away the gas in the very birth cloud in which they were born. And so if the gas gets thrown out of the galaxy, then again the star formation will stop. So understanding star formation uh, in this kind of qualitative way is relatively easy, but trying to do it in a quantitative way is difficult. What happens when two galaxies collide? This is a question that I'm going to answer in the next talk by showing you a simulation of the collision of the Milky Way galaxy and the Andromeda galaxy. Why galaxies are essentially two-dimensional, except for spherical. So it's only the disk which is two-dimensional. And one of the reasons why the disk is two-dimensional is because it is a rapidly rotating system. Okay, and so there is a net angular momentum of the system, which is of course perpendicular to the rotating disk. So if the system does not have a net angular momentum, or if the net angular momentum is very small, in such situation, you will not get a two-dimensional structure. You will get a three-dimensional structure. You like look at the solar system, for example. Almost all the planets, they are revolving around the sun in almost the same plane. Okay, so the solar system is also essentially a two-dimensional structure formed by the rotation of or revolution of planets around solar system. Yes. Why are most of the globular clusters found in the halo? Okay. Uh, one should ask think of this question a little differently. One should ask the question: are there any globular clusters which are inside the disk of the galaxy? So globular clusters are structures which would, if they what do they contain? They typically contain a large number of stars densely packed together, and many of these stars, or most of these stars, are old. Okay, so the globular clusters form the bulk of their stars at early times. Now, why don't globular open clusters exist in the disk of the Milky Way? Why don't globular clusters also live there? The reason they don't live there is because these kind of coherent structures, if they were to fall into the Milky Way, they're self-gravitating systems, they would get tidally disrupted. So that is why you can't form a globular cluster outside and put it into the disk as is. It will get destroyed. What about stars, which are old stars, which are there in the Milky Way disk? They're there, of course, like the sun now also is a middle-aged star, but that is already in motion around the center of the galaxy. It is not an independent gravitationally bound system like the globular cluster. So that's why you can't form globular clusters in the disk at all. And any globular clusters that try to fall inwards will get tidally disrupted, and all the stars will get strewn about. You won't have that coherent, dense structure that you see in the globular.